Hello everyone, today I am presenting my project called Dynamic Memory Management Visualizer. The main goal of this project is to help students understand how memory works inside an operating system in a visual, step-by-step and interactive way. Many students find topics like tagging and segmentation confusing, so I created this tool to make them simple, visual and easy to understand. When we open this project, we can see modern user interface with the navigation bar on at the top. This project is divided into three section: tagging, segmentation, virtual memory. Each section focuses on one important concept of memory management. Tagging. Tagging is a technique used by the operating system to manage memory efficiently. In tagging, logical memory is divided into small fixed size blocks called pages. Physical memory RAM is divided into blocks called frames. Each phase is loaded into a frame when required. Now let's understand some important terms. Page fault: when a required page is not present in memory. Page hit: when the page is already available in memory. Page faults are slow because the system has to load data from disk. In input section, in this section, the user provide a page reference string which represent the sequence of memory access. Number of frames which represent the number of available memory slots. Animation speeds to control visualization. Now FIFO. FIFO, the page that comes first is removed first. It works like a queue, simple but not efficient. LRU list, recently used. The page that has not been used for the longest time is removed. This is smarter than FIFO because it considered uses history optimal. In optimal, the page that will not be used for the longest time in future is removed. This gives the best result, but it is not practical in real system because we cannot predict the future. As you can see, when I click the run FIFO button, the FIFO page replacement algorithm start executing. FIFO stand for first in first out, which means the page that entered memory first will be removed first when the page new comes. Here the memory visualization sections. These boxes represent memory frames. Each frame stored one page. When a new page comes, if there is a space, it get added. If memory is full, the oldest page is replaced. Each step is slowly cleared. Currently memory state which phase is coming, whether it is hit or fault. Fault means the page was not in memory. Hit means the page was already present. This helps us understand how memory efficiently. Step 6, page 3 fault. This means page 3 was not in memory, so it had to be loaded, causes a page fault. So overall, by clicking FIFO, we can see how pages are replaced, how faults and hits occurred, and how memory changed step by step. Now we can come to graph section, which help us to compare algorithm visually. As you can see, the first graph, it shows page fault comparison between FIFO. Each bar represents number of faults and each algorithm. Higher bar means more page fault, lower bar means better performance. Heat comparison. In the second graph, it shows heat ratio. Heat ratio means how many times required page was already in memory. Higher percentage means better efficiency. Lower percentage means poor efficiency. When we click run LRU button, the system process the input page sequence and manage memory frames according to LRU rule. LRU means the page which has not been used for the longest time is removed from memory first. How it works: when a page request comes, the system check if it already in memory or not. Case 1, page is already in memory, no page fault occurred. Case 2, page is not in memory, page fault occurred. If memory is not full, page is simply added. If memory is full, LRU algorithm find the page that was used least recently and removed. Graph visualization. If the graph shows, it represents how memory frames change each step of page execution. Each step shows current page in memory, When replacement happen, the recently used page is removed, new page replaced in virtually. Now when you click run optimal in your project, you can explain it this. When we click run optimal, this the system process the page sequence and fill memory frames. Whenever a page fault occurred and memory is full, it removes the page that will not be used for the longest future. Graph. If a graph so x axis time or page sequence, y axis memory frame, each block pages in memory. When replacement happen, the system remove the page that is least needed in future. New page is inserted in it. The graph shows how memory frame change based on the future page. Now I am showing the segmentation module. What is segmentation? Segmentation divide the memory into logical parts called segments. Three parts: code, data, stacks. Now move on address translation. Base address, it is the starting physical address of the segmentation. If the base address is 1000, the segment and start from memory location 1000. If the limit is 2000, it represent the maximum size of the segment. If limit 2000, then valid address are inside the range only. Offset means distance from base address. It is the address requested by the user inside the segment. Memory segment visualizer. This screen shows the segmentation memory management process in a visual form. In segmentation, memory is divided into logical parts called segment. Each segment has base address, starting location from segment, limit, maximum size of segment, current example on screen, base address 1000, offset 5. This screen bar visually shows the memory segment starts from the base address 1000. The mark offset plus 500 indicate the request location inside the segment. Address translation address translation. The operating system convert logical address into physical address using the formula physical physical address is equal to base plus offset. Like example, 1000 plus 500 is equal to 1500. Therefore the final physical memory address is 1500. Now status. This result shows safe access with bound. This means the process is accessing memory logically and no segmentation fault occurs. Now I am showing virtual memory. What is virtual memory? Virtual memory management technique that gives application the inclusion of very large continuous main memory combining RAM and disk based secondary memory. Why virtual memory? Run program larger than physical RAM. Each process gets efficient sharing, simply linking. Key terms: physical virtual address, physical address space, table, MMU, TLB, swap space. Demand pays. Pays are brought into RAM only needed if the reference space is not present. Added translation. CPU immediates a virtual address split into number of bytes offset. MMU check TLB on miss it work. If not, page fault OS load space from disk. Tracing means a system spend more time swapping page in or out. Efficient access, it is equal to 1 minus p into memory access into p into page fault time, where p page fault rate, even p hurts performance because page fault. This is a advantage is logical address space isolation, multi-programming on demanding. Thank you.